Again, I am happy to welcome you to the Learning Journey Hazard and Risk Assessment. My name is Tony Jör. I am working as a TR advisor with Swiss Red Cross, and I am also a member of the core group of the Swiss NGO DRR platform. Um, I've seen many of you, are for the second or third or fourth time. So you know the drill, the etiquette. We are recording, and we do that for all the sessions in plenary to upload it on the platform webinar on the platform website afterwards, and to keep it for people who want to listen and watch it later. And please keep your mic muted, but you are invited and encouraged as always to keep your camera on at all times if your bandwidth allows that. And with the questions, you can you can ask them either by raising your hand or by using the chat. The webinar today is the fourth module of the learning journey, use of drones. And the learning journey consists of two parts. The first is on hazard assessment and has the objective to enhance our capacity as practitioners so we can independently conduct a hazard assessment and know how to retrieve airborne data. It consists of 5 webinars from March to May, and in September, we don't have the date yet fixed, but we will keep you updated. We plan a field day on hazard assessment, and this will be a great opportunity for those of us who are based in Switzerland or happen to be in Switzerland to practice and consolidate the learnings of the webinar series. And we will keep you updated. The second part of the learning journey will focus on risk assessment and cost-benefit analysis with 3 webinars that we have planned in the beginning of 2024. And that's it from my side. And I am pretty sure that everybody now knows already Andrea. So I'll just hand over directly to Andrea, please. You have the floor.
I'm still muted. Okay, now. Hi, everyone. Well, I was just checking if the slides are visible. Yes, good. Thanks, Tony. Okay. Well, yeah. So I am Andrea. I'm here today to tell you a bit more about drones. Last time you had me here on this learning journey, we talked about satellite data, GIS, and we covered a lot of terms that are important in this field. And today it's all going to be about drones and how we can fly the drones in order to create some of the data that we need for hazard and risk analysis or other things as well. And I thought it would be a good idea to start with a quiz right away or a little exercise just to get our brains back into the topic. And it's an image word puzzle where you'll be put into groups and then you join. Once you're in the group room, you end up on the slide of your group. If you're group 2, you go on slide group 2. If you're group 1, you go on slide group 1, etc. The link is already shared or will be now shared. Yeah, shared already by Nora. Thank you. And the task is to match images with the words. There are many, and it's not as simple as here on the example, but you just drag your word onto your image and we'll see who gets them or which group gets most of them correctly. Is everyone back?
Mm-hmm. Is this the solution what you have there, Andrea, now
That's
on
the
the screen?
solution, yes.
Okay.
Andrea, we couldn't move the either these images or the text box to the relevant position. So
Ah,
we just discussed which belongs
Yes,
to what, but we couldn't move
oh,
it.
okay.
Okay,
yes,
we
but it
could.
was fun.
Uh-huh.
We had
Just like
only
Oh, it's true. Yeah, I
Laserzugriff.
can't move it here either. Ah, okay. Well, no problem. As long as you guys had something to discuss with each other, it still makes sense. What
Yeah.
you see right here now is the result. So this was, and I just took the examples that we used in the previous slide decks, etc. So we're not getting too confused with trying different stuff. But the goal was just to revoke the terms map scale, resolution, GIS, raster data, orthomosaic, georeference, digital elevation model, vector data, and contour lines. There is someone with a question, yeah?
Just an
Walter?
observation, Andrea,
Yeah.
if you agree. I was at the same time processing data on Pix4D, so that was the reason that my laptop is working very, very slow. I don't know if for anybody else has the same observation, so I just quit the processing of the data to have a sure access to the presentation.
Okay, that's weird. Well, yeah.
And we had Walter who raised his hand, but
Yeah,
Yeah.
just Tony, I just wanted to bring the question about maybe the resolution could be a little bit more explained because it was the last one we had and we didn't quite connect it. We just came to resolution to this image just because it was the last one.
The last one. Ah, okay. Resolution. So you want me to explain again what resolution
Yeah.
is
What
meant?
does
Okay.
the dog and the bicycle have to do with resolution?
It's true. It's true. Maybe far-fetched if one wasn't on last time's session or so, or yeah, it just also flicked through. So the idea was basically when I explained resolution last time, I meant to describe on how many pixels you need in order to recognize an object. That's why there is the dog and the bicycle, which are different sizes of objects basically. And a smaller object, you would need a higher resolution in order to recognize it's in it, since it would need a camera that captures that object in more pixels than necessary. You would need we said 3 to 4 pixels to identify, to detect, sorry, 3 to 4 pixels to detect. So an object can only be seen if it's represented by 3 to 4 pixels. If you want to be able to identify what type of object it is, you need around 6 pixels or more. And that will then again, so if you want to look at a car, you would have to take a satellite image or a satellite image with a high enough resolution so you can recognize the car. If you pick a satellite image that has a resolution of 20 meters per pixel, your car disappears within that square. It won't be recognizable. However, if you then pick a satellite image that has a resolution of 1 to 2 meters or so, you're then able to recognize your car. So it's important to understand what do you want to look at in your final output data set, and at what level are you collecting the data? At what one could almost translate to detail, but since we're working with sensors like cameras or LiDAR data, etc., it's better to use the word resolution and refer to centimeter per pixel. Does that answer your question, Walter?
It does. I thank you very much.
Cool. Good. Okay. Drones. We're gonna look at the types of drones there are. the equipment that one needs to fly a drone, how the data creation workflow looks like with a drone, how data is being processed, and some examples of applications. Now, what does it take to become a drone pilot in the first place? So many may think that it is very difficult. However, I can tell you the flying is the least difficult part. So everyone can do it. It might challenge a bit your physics abilities, your weather forecasting skills, your navigation and orientation skills, and your camera operation skills. Those are the skills that if on any of these you have more experience, it will already make that part of the workflow easier for you to handle. But even if you have no idea about any of it, today's tools are made in a way that they pretty much help you understand on the way or show you a message that makes you understand, etc. Or even limit the use. The drone, for example, as soon as it hits one of its limitations, it may trigger an automatic reaction and just land or go back to the home waypoint, etc., without you actually having decision power. So it will just overwrite because it detected that this is not a good situation. And then, of course, you need a drone and a controller and good weather, and you can go practice flying. Did I have another one? No, I think that's it. That's just for being the drone pilot part. Not much required. We will see later in the slide deck that there are a couple things that are good to be aware of so we don't endanger anyone that is around, whether also in the air, helicopters, gyrocopters, or other aircraft, or then people on the ground, children playing, etc. We don't want to hurt them by having stuff fall on top of them. There are different types of drones. Some of the most common ones are here in the middle, the copter drone. That has become very accessible and cheap to get these days. Then we have the next ones would be a fixed wing drone, a drone that has only one propeller and uses its wing. Basically, it's one wing. All the surface that creates a lift is called one wing, where basically each propeller of a copter is also called a wing, but that's something different. But yes, so we have fixed wing drones, copter drones, and then the VTOL fixed wing, where the word VTOL stands for vertical takeoff and landing. We'll see that again. And technically, a copter drone is also a VTOL drone because it also takes off vertically and lands vertically. Okay. In terms of copter drones, they can be very small. They fit on a hand, and the propellers fit nicely in, and they are very light. One can put them in a backpack, bring them everywhere, and carry them around. Or then they can be up to 15 kilos or heavier, of course. With all these parameters, by the way, I stay within a bit the normal things that we can do. Of course, if we look on the defense side or the military side or special government stuff, it's huge. It might even need a runway, etc. But we're not going down that rabbit hole. We stay on the civil application side and around the areas and topics that sort of are interesting for us. A copter drone like that can cost anything from a couple $100 up to $100,000, I'd say, depending a bit also on what type of payload is being put on. A payload is basically the amount of material that can be put onto the drone additionally. And in most cases, when we're talking about drones and aerial mapping, payload means camera or sensor. You would get around 10 to 30 minutes flight time out of it. Yeah, There are by now some copter drones out that cover or can fly 60 minutes. However, then we already reached a more expensive side of the range. Wind resistance is around 20 meters per second, and that's in kilometers per hour, that is 72. So they can fly in quite strong wind. However, if you want to do any mapping, so for mapping, it's first of all not good to fly in too much wind. If you fly otherwise in that much wind, you still risk that you lose your drone because it's just being challenged too much, depending on what kind of turbulences happen and what area you're flying in. If you're doing a mapping mission, you will see exactly how this works later on, but it's basically a lawnmower pattern going up and down, so you get enough overlap between the images. We can cover around 100 hectares. The speciality of a copter drone is that it can hover in a certain position. It can stop in air and maintain its altitude without moving forward. This is, of course, very interesting if one wants to do an inspection, for example, of a bridge or another structure. One wants to fly to a spot and look exactly at that spot, a whole position for a while until one recognizes what one needs to do, and then one flies back. Another application is anything that is search and rescue. So, so there are two types of search and rescue. Of course, if you have no clue where someone is, you also end up doing a lawnmower pattern looking for someone. But if you know approximately the area, you might just send a drone there looking in specific places, and maybe even carry a thermal sensor to capture a thermal response from the person. These days, there are also sensors that can capture the signal of a mobile phone. Even though there may not be a network, that sensor will create like a mini antenna and can receive the signal from the mobile phone of the lost person, and this person can be found in this way. Any questions so far about the copter drone? If not, we're moving on to the fixed wing ones. The cost goes a bit up. They're usually already on the professional side. Flight times is around 90 minutes, and they weigh usually up to 2 kilograms. Everything that's heavier than 2 kilograms becomes unpractical to launch. There are some systems, but they are using a catapult. So you first have to set up a catapult with like rubber bands, really, and then you flick the thing into the air. But it didn't prove to be very practical. We have wind resistances here a bit lower than with the copter systems, just because there are less motors and less propellers that can fight against the wind. So we're looking at 17 meters per second, which is around 61 kilometers per hour, which is still a lot. I mean, I'd probably only do a mapping mission in 8 meters per second wind, which would translate into maximum 35 kilometers per hour to 40. Of course, one can always push it, but the recommendation be the calmer the better, because the drone is not being flicked around as much. If the drone wobbles a lot in the air because of the wind, your images may be affected, and therefore also your result at the end. The specialty with these types of drones are the forward, the coverage. They are very efficient in flying, same as in real aviation. If we're going from Switzerland to Australia, we're not using a helicopter, we're using a fixed wing drone. And that's for the simple reason that this type of shape is aerodynamically more efficient and therefore can fly better, longer, without needing as much fuel or power or battery power. And therefore that explains also the application is mainly wide area mapping. So what did we have here? The 250 hectares at 120 meters. And there is where we will get back to that again, but it depends what altitude you're flying at. However, you oftentimes you're restricted to the 120 meters above ground. But the flight planning software will also tell you that that's not a problem. Of course, I'm forgetting to say my next word here. If the higher you fly, the more area you can cover, but you're losing the resolution, okay? Because you're further away from the surface you're looking at. It's like taking an image of a person's face from very close or from very far. That's basically the difference. And so you need to choose whether you want to cover a large area or very large area in one flight, or if you need really the high resolution to recognize small objects. Then we have the hybrid, which is a VTOL fixed wing. Same cost around these days as the fixed wing one, with flight times around 90 minutes and a weight of around 4.5 kilos at the moment, and the wind resistance also similar to the fixed wing one, 17 meters per second. The mapping area coverage can be much larger though. We're up to 4 kilometers square. And that's mainly due to the type of sensors we can carry with these heavier systems. Imagine the smaller the drone or the smaller the flying object, the less weight we can carry, the smaller the camera has to be basically, and the less resolution we get. So with these type of drones that can carry more, we can put heavier sensors or cameras on it and therefore cover much larger areas. Thus, we have the advantage that these systems can take off and land vertically. A system like that always needs sort of like a little runway space, like a football field or so, that is free of any obstacles, because it needs to do a linear landing and also basically a linear takeoff like a real aircraft. Here we take off and land vertically. Applications are also wide area mapping. Any questions about the types of drones?
Yeah, Andrea, comparing the fixed-wing drone with the VTOL fixed-wing drone, where is the advantage of the fixed-wing drone? Because I see costs are the same. Flight time is...
The size would be potentially an aspect. You're more flexible, you can carry it more easily somewhere, where with these systems, well, the box is a bit bigger. Yeah.
Okay.
Mm-hmm. But yeah, these days the VTOL fixed wings have really caught up. You may also know the Wingtron drone, which is the orange one. They basically take off vertically and tilt the entire body then to horizontal. So their body takes off like this and then drops over, which is also a variation. No conclusion yet on what's really better, but that's the systems out there. Any other questions? If not, then we're looking a bit at respecting operational limitations. So as I already mentioned a couple times, the drones or aircrafts, they can only fly in certain conditions, and that's called the flight envelope. I put one here so you get an idea of how this looks like, and it's basically just the amount of G's created, G as in gravitational force when an object that goes at high speed doesn't turn, or a turbulence hits it, etc., then these g-forces, they apply, and each structure of a flying object can only take so much. It's built for a specific amount, and if it's being accelerated or pushed too much over its limits, the structure will crack, fall apart, and the system crashes. And basically what one is looking to do is to always be within this green section of the flight envelope. If one ends up in the yellow or orange parts, it's not so good, and one better hurries up to get back into the green part, and the red part would mean you're probably losing your drone. So, and a big impact, of course, on this has the weight of the drone. It's all manufacturers currently out there are maxing out on what they can give. So it means you cannot actually put more weight onto the drone. And the weight is also distributed in a certain way. Here you can read aloud ZG from leading edge. ZG means center of gravity. That's basically if you would take the drone and balance it on your finger, the moment that you manage to balance it, that's where its center of gravity is. I don't have anything small enough here to demonstrate. You can try it with any object, actually. But yeah, if you put then weight on the front or the back, the balance is off and it tips, and that's it. So it's not a good idea to put other stuff on the drone that there already is. It might still take off, fly a bit, but most likely crash after a bit of time. The other thing that influences a drone's or an aircraft structure is the maximum flight altitude. The altitude, of course, with altitude, you may know that we are losing, that the air pressure goes down, atmospheric pressure goes down the higher we go, and that also has an influence on the flight and the aerodynamics of the aircraft. So you always have to make sure to be within the limitations that are given on the technical data sheet of these drones. The third thing would be the radio link, command and control. That's the link that is being used to talk from the ground station to the drone. And you can see this one has a very long range of 5 to 7.5 kilometers. But my assumption is that at 5 kilometers, you're already reaching its limits. You lose the link, and then you lose communication to your drone. You will not know its position. You will know nothing about it. You will just be flying blind if it is still flying. Wind tolerance, this is what we talked about already. It's important to stay always within the tolerances that are given in the data sheet of these drones, no matter how high or low they are. Otherwise, you're risking to break your system. What usually happens as well is that the drones on their controllers, they have built-in information warnings that are being triggered once the drone detects that the wind speed is too high for it. It will give you a warning and say, we're too fast or too slow, we're too fast, it's due to the wind, and it will either have an automatic reaction just by coming back to you, or then it is so strong that it cannot handle it, it will decide to just land wherever it is. Or if it's not that strong yet, you can tell it what to do. You still have some power of command over it. Okay. Any questions about operational limitations? Also want to say they are public. That's not a secret. You don't need the user manual of the drone to understand what they are. They're usually published on the websites where you can buy these drones. and you can already then check out, okay, am I going to fly in an area where the drone needs to be able to fly in these circumstances or not? Does its operational limitations play a role or not? It's always something good to analyze. Equipment to fly a drone. We need a ground control station, where here I'm showing you the very fancy one. It's a smart controller, they're often called. They have everything integrated in one system. It has the flight control and monitoring software playing on a screen. Most of the times it's an Android. I'm playing on some sort of a tablet. Here it's fully integrated with some control sticks. Not all drones have control sticks, especially the fixed wing ones. You will not have any sticks with which you could operate or tell the drone in a certain moment what to do. That would all happen in the flight monitoring software. You can see here that we have those two antennas in the back of the controller. Those are there to set up the communication link with the drone during the flight, so that you as the pilot can take control over it. Another option for ground control stations are that you, for example, get only this top part with an attachment option for the phone. It means you download an app on your phone and then you clip the phone onto the rest of the controller part with the antennas, etc. And then you have your flight operation software on your phone, and you control the drone with the sticks and you see what's happening on your phone. And another option would be to use the laptop. It could be that the flight operating software is on your laptop, and you get a separate device for the antenna that you plug with a USB or with a USB cable that then sets up the communication link. Then, of course, you need the drone, be it a copter, a fixed wing, a VTOL drone, etc. On here, you have your camera and your batteries. It's important to have enough batteries depending on the system you're choosing. You might pick one that flies 10 minutes, but then you notice, I want to do a project that takes 30 minutes. So it means I need 3 batteries. And then, of course, we need some manner to save the data. So most of the time this happens via some sort of SD card that is either on the drone or on the camera, and then it's just being transferred after the flight to your processing station. That the transferring can happen via simply taking out the SD card and put it in your processing computer via a cable or a wireless transfer. But most of the times it would be either via a cable or an SD card, just because it's much faster to transfer the videographic or imagery data on the processing station. And we'll look at that in terms of requirements a bit later on as well. You can process on a desktop computer, a laptop, or then just send it all up into the cloud and process online. That depends. There is no better or worse. It just depends on your situation that you have at that moment. Any questions about the parts of the equipment?
I would have one if you allow me. Just, with the data, we're talking about how much data? Don't say it depends on the time, no, but as an example, so I can imagine, what does it?
So what did we download? We downloaded 100. There was 100 to 300 images you take easily with a drone. You end up usually with the, let's stay on the small copter drone side of things. You end up with a couple of gigabytes, let's say 5 gigabytes of imagery data. You need to be able to copy that, and then you transfer, well, you still need additional storage space to then save the processed data sets. So your orthomosaic or your digital elevation model, etc., is again a couple of gigabytes big, usually.
Okay. Thank you.
Yeah. And it's laughing because it's a hard question to answer, because it really depends on the sensor that you have on your drone. If that's a very big camera, if we're talking medium frame format camera, that would be a large sensor. You have like 150 megabyte per image, and you're collecting it. Yeah, that's a different story than when you go for a small sensor, maybe 1-inch sensor, where one image is maybe 15 megabyte big, and you do a couple thousands of those. It's a much smaller data set to handle. And the range is really, can go from anywhere. On some of the VTOL fixed wing that we saw, the biggest sensor at the moment is a full frame sensor. And full frame sensors, of course, what was it? 14 megapixels and full frame. So you get a couple hundred gigabyte of data, and then you very quickly add the storage space of 1 terabyte that you need. That's it. Yes. Yeah. But we can talk about this a bit more as well. But I'm not saying it to scare you. If you're flying, like what we're gonna probably do on the field day, you can handle it with a 32 gigabyte SD card, or even a bit smaller. It would just be important to have that space also available on your processing machine if you're planning to process on the machine, because processing from an external device will make the processing much longer, because the computer will have to read and write additionally. It has to read like twice. Oh, any other questions? And did I answer yours, Tony? Cool. Regulations. Some things to be aware of, not to be scared of, but aware of, is privacy. Maybe don't go fly around your neighbor's windows and check what they're doing unless you have asked them if you're allowed to. Avoid controlled airspace around any bigger airport. There are at least 5 kilometers you need to stay away from, all around. By now, there are lots of resources out there to check what the airspace, where they are. And in some of the flight planning software, this information is even integrated, and you can see if you're actually allowed to go there or not. Avoid any smaller airfield as well by 5 kilometers radius. At the moment, in terms of flying drones, you always have to be able to see your drone. This is called visual line of sight. You're basically not allowed to go beyond visual line of sight. So you always need to be able to see it. And in most countries, you have to stay below 120 meters or 400 feet above ground, because at 150 meters, that's the lowest that aircraft and helicopters, so manned aircraft and helicopters, can fly at. So one has built in a bit of a buffer that one does not interfere, like it's also done in aviation, travel aviation, you want to call it, where the airlines are also separated by 500 or 1,000 feet in order to make sure that they surely not go into each other when they go through those airways. If you choose a drone, at least for Europe and in the US as well, that is heavier than 250 grams, you need a drone operator's license and liability insurance. Just something to keep in mind, depending where you're at in this world, just check with your local civil aviation authority. On the web page by now, most of them have some guidelines around flying drones and what you need to do that. Any questions around regulations? I just wanted to do this quickly and no need to go into it in detail as we're hopefully not challenging that system for now. Traveling with drones, I thought maybe that happens for one or the other one for you. If you bring a drone with you, it has to go into check-in luggage. Use a hard case or something, then it's best protected. The batteries, however, need to go into your hand luggage, best inside a LiPo-safe bag. Those bags you can get at a hardware store or so, and they're specifically designed to contain a battery fire. LiPo batteries, so lithium batteries below 100 watt hours don't require approval to bring onto a plane usually, and you can calculate your watt hours by multiplying. It's usually milliamperes that you find on the batteries divided by 1,000 to get the amperes times voltage, which is also mentioned on the battery label, and that gives you your watt hours. Many these days have directly the watt hours, so then you just need to remember that you want to be below 100. Okay. Of course, always check with the airline that you're flying with in case they have special rules, but most of them, yeah, stick to the same these days. Any questions? If not, then we start looking at how to create data, like the orthomosaics, the digital elevation models, the contour lines, etc., with drones. Apart from just flying them around, we can fly the drones in a way that we actually map an area. I already mentioned before, we can fly this sort of lawn mole pattern. Basically, it takes off. Here it flies to the edge here, flies up and down and up. And that will make sure, and while it's doing that, it's of course taking the images like you see here. Okay. Here the images are just nicely lined up, but basically you always have a certain amount of overlap between the images. And if we're doing this type of photogrammetry, we're talking around 80 to 60% of overlap between all images. That's a lot. If you have, that's more than half of the image will be basically taken again. So we need to plan our lawnmower pattern, then get out, fly the lawnmower pattern and collecting all the data. And then we process all that data, and then it's ready for analyzing. During the processing, where we apply the photogrammetric algorithms to create a 3D point cloud, an orthomosaic, or a mesh, etc. Okay. I see we're almost close to the hour here. I suggest I do a quick 5-minute demo of one of the flight planning softwares out there, and then we have a little break. Does that work for everyone? Okay. I just need to switch. Okay. So now you should see a software called Emotion. This is the flight planning software for the fixed wing drone we've seen before, where maybe the fixed wing drone is not the latest in trend anymore these days. The software is still very good. And basically it guides us through what we need to do. So we see here on the side, we are now on the welcome page and are looking now to go onto the mission page, where if we want to build a new mission, we just need to pick the camera. You see, they have many. Now we go with this one that is called Area X. It's just a standard RGB camera, and we say create mission. This brings us to the mission panel, where we have a map background and where we can choose where we want to fly. I thought maybe we go where we might have our field day. Not exactly sure where, but I believe somewhere here would be the valley. Is that correct, Georg? I assume. Voilà. This software also has a 3D view, so you can see this is pretty mountainous. It's like Google Earth, nothing too special about it. I'll switch back to the 2D view. You see it turned now because it just turned the map again to face north. So at the top of the screen right now, we have north. Okay, we can just work our way through these tabs here. And basically, in most software, one has to define a so-called working area. So it means the drone has to stay within this circle and is not allowed to fly outside of this circle. The circle does not only have an extent, it also has a height. Right now, the altitude is set to 120 meters above ground, above elevation reference. Okay. Good, we can do takeoff and landing. Yeah. It's a fixed wing drone, as I said before. It requires like a little football field technically to take off and land. I'll make it a bit bigger. Voilà. So we have that. And now comes the interesting part. So now we're defining the mission block or the lawnmower pattern by just picking here this item. It's not important what they're called in this software. It will be in all the software, different flight planning ones, it's called differently. But the important part is you draw this polygon like I just did, and then it calculates for you the flight path. And you see it's parallel flight lines going up and down and up and down. Now, I'll show you something. And yeah, also most software will be able to do that. If not, they will tell you that you're crashing into the mountain. But it basically adjusted the flight lines to be at, what did we have here? To be at 120 meters above ground everywhere within that area that we defined. And this will give us 2.5 centimeter per pixel resolution, which is plenty for our application. We would also be fine with less resolution if we're looking at detecting any sort of hazards that are related to these gravitational slope events or flooding. Now I have a message here. You see, I broke the law. I'm way too high above my working area. So now either I say, okay, I have to fly lower, or I can say, I don't really care. And I just bump up the ceiling here, and you see it disappears. We also get an idea for the weather here, and this is not bad, 2 meters per second. We could totally fly. Today it's basically almost no wind. It would be a very nice flight day. Didn't mention exactly yet the overlap. I just want to do that quickly. So the resolution can be adjusted here if we're looking. And of course, you can do that in any software. If I bring the resolution down, of course, my lines are coming closer to the ground, potentially making it more hazardous that you fly into something. Okay, so it's something to keep in mind if you're reducing your resolution. The other thing you can change and is important are the overlap. There is a lateral overlap and longitudinal overlap. Longitudinal is along the line, along your flight line, and lateral is between the lines. We will see that once we do some test flying here. If we especially increase the lateral overlap, you see we get more and more flight lines. Of course, more flight times means more flight lines mean more flight time to fly. And yeah, then it depends again if you have enough battery to do that or not. But we can leave it at the standard for now. Okay, shall we take 5 minutes break, and whoever has questions can ask questions, or we can talk about stuff meanwhile. And then I'll show you a little flight simulation so you get a better understanding of what I did just here. Little break is good.
Yep, let's be back at 11 after 2 when you say 5 minutes. Is that okay?
Yeah, yeah.
Okay, good. Thanks. Thanks so far, huh, Andrea.
Okay.
It's very illustrative, huh, this software. You know, you can really feel it in the terrain. That's great. Wow. You're muted.
And you can have on your laptop. That is nice. Which is more practical for our situation. Of course, if I now have to work off a controller, that would be a bit more messy to show.
Yeah. But there, you know, when you say like you're not allowed to go more above 150, not in such valleys that nobody cares there, or how is it? You know, are we there quite practical, or what is? Because you're higher.
The problem
No, you're
is
not
just the
higher.
other air traffic. And in the mountains, it can totally be that you have crazy helicopter pilots that zoom around the corner of a mountain and end up being lower.
Okay.
There are ways these days to have an eye on this. I mean, one is pretty simple. You have on your phone your flight radar in 24. It's just an app, and every aircraft that sends out an ADS-B signal is being tracked there. So you can hopefully see them. But if they have not turned on their transponder, you won't be able to see them there.
Okay.
There are little detectors as well, like we used to use an ADS-B receiver, which is just a sensor you plug via a USB cable to your computer or your flight controller, and then it shows you other air traffic that is nearby. But it also requires the other person to send out a signal for the other aircraft, if it's a helicopter or so, to send out the signal. And you'll never get around having a spotter with you. So it's best to always have a pilot and a person that has the brain space and the eyes to watch out for other air traffic. And if you happen to be in the air at that time, ideally you then spot other traffic and then you just pause your flight or you make your drone. Oftentimes it's just a matter of bringing the drone lower, because an aircraft never voluntarily wants to go that low to the ground. That is really dangerous, because the lower you are to the ground, the less time for the pilot there is to react in case something happens.
Mm-hmm.
And yeah, same for the helicopters. Right. Yeah, but yeah, it's not super practical yet for anyone, but regulations are just not there yet. And so for aviation and the EASA and so on, they don't like the drone space so much.
Mm-hmm. Mm-hmm. But probably now that people are again back and maybe listening, um, just a bit to answer my question there, you said something and I didn't catch it 100%. The software told you, hey, that's not possible, you need to do something, but that was like something, you have to go higher up.
Yeah.
And
So
there, but that's not the same thing, because the drone is never higher than 120 meters above ground, right?
above, yeah, yeah.
So there you don't break the law, huh? But what
Yeah,
is it
no,
with this circle higher up, with this radius? I didn't get
yeah.
that.
So this circle is basically just there to limit where the drone can go. In this software here, the engineers who built it have not managed to make the circle adapt to the terrain. Technically,
Oh,
the
okay,
circle
yeah.
should be, yeah. So what
Okay,
it
so that's
does is
just a.
yeah, it picks the center of the circle
Uh-huh.
as a
Okay,
reference.
so
So
that's
of
just a
course, if I'm
technical.
here or here I'll be below and here I'll be above.
Uh-huh. Yeah, yeah. Oh, okay. Now I understood it.
Yeah.
Uh-huh. No big deal. You just have to understand how it works, and
Yeah,
then you
yeah,
just adapt,
yeah,
huh? Yeah.
yeah.
Okay.
And that's
Thanks.
why it's good to go practice somewhere very safe. Yeah. I just had the comment about running to fly a drone in Bangladesh requires ministry level approval. Yeah. There are countries where this is unfortunately the case.
Um, Sanjeev, do you know why? What would be the rationale behind it?
Simple
Just
sentence: security.
okay. Okay. Uh, Well, it is quite densely populated, Bangladesh, right?
Yeah, and drones. I mean, it has a camera. You can go anywhere you want and look at stuff that some people don't want you to look at. That's
Yeah. Uh,
that can be a problem in certain areas. There are even, I mean, if you get close to borders, in war zones, there are often there are GPS jamming. So it means they're blocking the GPS signal to come in, and that's essential for the drone to fly and know its location. So if the drone then enters such an area, most systems, they crash. By now,
Could
there
be
are drones out there
could be
that are,
misused too.
hmm?
In Myanmar, you're not allowed to have any remote controlled toy, not
Yeah.
even a vehicle, because they could be misused also with transporting explosives.
Yeah. No, definitely. Well, it could be misused. However, it's not so easily done, as I explained. At least with the off-the-shelf systems, they're already at their weight maximum, so putting stuff on top is not really an option. But of course, there are many people also buying all the material to build their own drone in their garage, and then you can build it in a way that it can carry what you need it to carry.
Mhm.
Yeah.
Maybe I'll just follow the chat. Niraj, he asked, you know, if this you've seen it probably. Yeah. Okay.
Yeah. So yeah, this software works anywhere. Yeah. You can. Now we're not gonna test it for all, but there is what was it? Nepal. We want it. And people have been flying with this software in Nepal as well. Wow. It just needs some time now to load the background data. That's why it's a bit blurry. But then, yeah, you could fly it here, as long as you're receiving your GNSS signal and it's not being jammed or so, or you end up in an area where that would be the case. And yeah, there should be. Yeah. I should also be able to share this software if someone has interests. No problem. In the end, it's a good learning tool. So, ta-da, I wanted to show you how the simulation works. But we can, at least in this software, one can start the simulation. I assume everyone is back from the break. Yeah. Okay.
Pre-flight checks completed.
Okay. Pre-flight checks completed. You see now it placed a little simulated drone here onto my field. It has a takeoff space, and I just need to make sure it. Takeoff. No, it should be enough space. We'll see. Okay, and I can assign it the mission. It will look like that. So the drone will take off and go to its area and map it. Okay, so it's basically now simulating.
Caution. Motors will start spinning.
It will simulate a fixed wing takeoff. So it needs some forward flight in order to take off. This one is also pushed by hand in order to gain altitude. You see here the live data, the simulated live data of the drone, which is now at 40 meters above takeoff. So above where it was just thrown in the air. Now it's 60 meters and climbing to mission altitude. Now I'll just speed this up a little bit. It first climbs.
Warning.
Yeah. It sometimes doesn't like to be sped up on the simulator. Okay, it reached basically the mission altitude. Okay, it's doing its first turn. We can see it's at 150 meters above takeoff. ATO means above takeoff. You can see it's flying at 1,130 meters above mean sea level. Yes, if the wind strength changes, so right now here it's a simulated wind speed. Of course, it's estimated here based on the weather forecast for this location. But if it changes, it will recalculate its flight time that it has or the time it takes to come back. This is the case for most off-the-shelf systems these days. And you can see here now, we're taking those pictures. I'll go a bit faster again. Look. I just let it take. And you can see if I click here, oh, and here, you see how much the images are overlapping. And of course, there is also the images on the line, they're also overlap to a good extent. And this is what we need in order to be able to process the data afterwards with photogrammetric software. Also, the location at which the images are taken, they are saved with the image. So basically, the image is geo-referenced. Not exactly, but it has at least a coordinate of the image. Like when you take these days an image with your phone somewhere, it often logs a GPS tag with that image as well. This one is just much more accurate. Okay, so if one would just now let the drone go do its thing, it would use its battery, it tells you how far it is from the home, it tells you what the link quality is, etc. If you're done or if something's not right, you can call it home.
Going to home waypoint.
This is also an action that often with any system, you have the go to home function, which just means the drone turns around and comes back to you or the ground control station in direct line. And usually once it's back to you, it stays at a certain altitude. This can always be specified, etc. Lena, what did you mean with your question? So this is just a simulated instance of the drone. If you're, of course, out in the real world and you're flying your system, you would see here in this software, like you see now the yellow drone, you would see it real time. So as well as you having eyes on it, you will see exactly where it is in the software as well. You will receive all the messaging and everything that it's doing or about to do, you get that information through. Voila. Now we can tell it to
Going
go
to
land.
home waypoint for landing.
Now in this case, it's doing a linear landing because it's a fixed wing drone. If it would be a copter drone, it could land just coming straight down. Go a bit faster.
Landing now. 50. 40. 30. 20. 10.
This is sometimes in the simulation it's not perfect. Anyhow, that's it. You've been flying, you collected your data, and now you're ready to grab that data off your drone from the SD card of the camera or connect with a cable, whatever is the system of your choice, and then usually follows a so-called post-flight procedure where you import all the data into a folder on your processing computer. One makes sure that the images all have their geographic reference tag, because that's very important for the processing later on. Any log files that come with it can be useful as well, just to keep maybe you have multiple drones and you're logging all the flights and you're monitoring where which drone is doing what, etc. Then you do the recording of all that data. And then we go off into the processing software. There were a couple more slides, but we can save the time. Does anyone have more questions regarding this process or this flight planning and flying mission? Most important, I think, to understand is that one flies this type of lawnmower pattern in order to have enough overlap between the images, no matter what drone you're doing this with. Right, data processing. So in order to process our data, we need to apply photogrammetry, where photogrammetry is primarily concerned with making precise measurements of three-dimensional objects and terrain features from two-dimensional photographs. Simply explained, it is the same thing what our eyes are doing. Stereo view, okay, we have two eyes, so we can judge the distance. It's like having two cameras that each one takes a picture and they actually overlap. Like our eyes see to both eyes, like the field of view of each eye overlaps. And the same principle is applied in those photogrammetry algorithms. It's basically the software will be looking for so-called key points in the images, which can be anything from a corner of the house, a little rock on the ground, etc. And it uses algorithms to be able to tell, oh, this item is the same as this item on this other image. So it will find on both pictures the same location, and then it can apply the different viewpoints to then intersect a 3D point. The parameters it's using here are the location at which each image was taken, and then the camera parameters. There are things like internal and external or parameters that are being applied. One other, for example, is that a small inertial measurement unit in the camera or in the drone, depending on the system, will record the orientation of the image while it was taken. Was it more like this or like that or bent, etc. So that's what it's using. And this will take us to the little exercise we had sent through beginning of the week. I'm not sure how many of you managed to install or try something with it. If your laptops don't have enough power, just go with the Pix4D cloud option. I picked Pix4D because they have a nice explanation and it's most straightforward in its use. There are open source software and cheaper solution, etc. But I thought since we can get 15-day trials on these, why not just go with that to try to understand better the principle of how processing such data works. Just switch again.
Ima? Kenno?
1 second, of course. Now this is struggling to load, doing too many things at the same time. Turn this off. Yes. Okay, no luck there for now. Okay, now I think it worked. Just relaunching the program. Schematic. Okay. Okay, sorry about that. It didn't want to cooperate anymore. So this is Pix4D-matic, and basically to create a project, it asks for images. Let's see what I can find. So ideally, I have now a folder. Which one should I take? Set this one. Okay. Okay, right. You specify a name for the project and the path where it should be processed, and you can click on Start. It also tells me how many images I just uploaded. And then it takes a moment to load those images. Voila. And basically what we have here on the left is a list of layers, and you will, once you've finished all the processing, you will be able to turn off and on these layers. And on the right side is more your the settings you choose to process, and the place where you can view a single image in order to make sure that it is correct. Voilà. Almost there. Voilà. And you can see the images have been placed on the map already, and that's because each image has assigned a geotag. Can I show that? Details. So the geotag can be viewed in the properties of each image. If you click under the details tab, there will be, you will find the coordinates of that image in latitude, longitude, and altitude. This is maybe also an important point. We talked last time about coordinate systems. Since while we're flying or in the air and capturing data, and we're using GPS data to create the geotags of the images, all the data that we are importing is in that very global coordinate system, the WGS84. It's not projected, it's just the latitude and longitude and altitude of the images. If you process like this and you leave it in WGS84, you wouldn't be able to measure or calculate a polygon because there is no such thing as square degrees. So you'd have to convert first to a projected coordinate system. You can see on the side we have here the different images. Click them. And we can see they're all in a good state. The processing steps that we have to now work through, we're not going to do it on this example because it takes a bit long, but it usually follows here this same pattern. Usually, if you have a normal project like this, there is nothing to worry about, and you just pick all the steps that you want it to do. You're not getting around the calibration, okay? The calibration has to happen, and only then you can pick also to densify the point cloud, to create the planes. Only if I have a densified point cloud and the planes, I can calculate a mesh and a DSM and an orthomosaic. You see there are different parameters, but usually the software will try to give you options like make it simple to then adapt all the parameters accordingly. There is a large scale and corridor map. It's a flat scene or with low texture that would, for example, be in agriculture, where if you mapped just a field with a lot of grass, then that would be quite low texture and a flat scene. Then there are the maps where high accuracy is important. There would be models where the 3D object is important, and Pix4D catches something of their own. Interior scene would be, yeah, you walked around your home, had your phone out and took many images, and now you want to create a model out of that. That's possible to do with this mode. Once you chose that one, after the calibration, we can then do a so-called densification of the point cloud. Remember before we said it takes 2 images to then calculate the 3D point. So there will be, after this first calibration steps, there will be lots of those 3D points, creating already a surface, but it will not look pretty at that stage yet. You will then have to densify that point cloud, which means the software basically interpolates points in between those initial points and creates a smoother, much nicer surface. However, it's not a polygon yet, it will just be points. Okay, that's why it's called a point cloud. And only once then we go to the DSM, the digital surface model, if you remember from last time with me, or the digital elevation model, that's when we are going from point information to raster information. So this process will create a TIFF file with pixels where each pixel has an altitude value. And only then we can create the orthomosaic, which is then the RGB representation of that area. Now, since this Matic here is not cooperating, I'll just switch again. Does anyone have any questions so far? Okay, so now we see a project here, and by the way, this is now Pix4D Cloud. It works the same but you don't have influence on the processing parameters as much as you do in Matic. So what we now just talked about, the calibration part, the point cloud, etc., and how these parameters are set, you don't have as much power over it, which is less interesting for someone who needs it very accurate or needs to have checkpoints, etc., in the project in order to make it all fit properly with whatever with other plans that he has. So I'm showing you here now the sorry, got lost. A project where you can see it does look a bit funny. So this would be the point cloud. And you also see that the points are actually very dense. Once it loaded all this up, we will recognize the features that are all represented by points. And you can also see that this is 3D. Like these are clearly roofs of something, of buildings, but we're struggling to see the walls. Huh? Okay. Just a minute. So we see the roofs, but here no walls. That's because we've been just looking straight down. So our camera position has been looking just straight down, not at an angle, and therefore we didn't capture enough information of the vertical surfaces. That's why point clouds from cameras looking just straight down always look a bit like that, where you could say, oh, this is not pretty or so. But there are multiple ways to work around that if one would want to have such a project done up very nicely. Requires more effort, more data, more images, etc. And for us at this stage, not very important, I think. Otherwise, we can look at it another time. So let's look at what we talked about last time. I'm selecting here on the left now the digital surface model. And in order to see it, I need to switch back to 2D. So this is the digital surface model. And it's colored by height. We can, well, I do know the region a bit, but actually red would be the highest spot here, and then going lower and lower down to blue, where blue is the lowest, and going back up here slightly, where there is another hill. From this, one could now calculate those contour lines that we talked about last time, for example. If I now choose orthomosaic, we end up with the RGB representation. Again here, it's 2D. I can't make this now move in 3D. That's not what it's made for. It's a TIFF file, and it's basically created out of all the images, out of all the single images that this project was taken with. That was 115. Once we have the project in this shape, we can, like most of these software, you can also create and measure polygon. And then we know we have a polygon here. We can, this would, for example, help to vectorize an area. It also gives us directly the surface of the area. And this is how we could go on and manually vectorize all the roofs or the outlines of those buildings, and then export them into our GIS software as a shape file or as a so-called a vector file, so polygons associated with the area that they're covering and their location. Same we can do with lines or circles or volumes, etc. But most importantly, we can just go and export files. Either we can export again the images, now in this case that we have them on the cloud. Sorry, that was a different project, so it had more images, but it would allow us here to download the orthomosaic as a TIFF or the DSM as a TIFF or the point cloud. All those points, the most common format, data format would be the LAS file, LAS. Do you have any questions about this part? Of course, there are many more details. We're zooming a bit through here. But I hope it sort of makes sense. And if not, then we'll take it back to
yes, Andrea.
Yeah.
I remember that the license is not that cheap. Would it be possible, what do you think, talking with Pix4D to get a platform, Swiss DRNGO platform license, because it doesn't make sense that each organization buys its own license, as it is cost it's expensive. But like a group license would be probably interesting.
That's definitely possible. We could pick up a conversation with them and ask what they have to offer. They do that for other NGOs as well. And that's totally possible that they give out those licenses. It is not what they have come up since back in the time, Georg. They changed their subscription models, and you can get now, they packed licenses a bit more into smaller subscriptions. So for a small Pix4D license, as for Pix4D Cloud, or for React or also Matic, you can just sign up and pay for a single month. And that's a maybe 100, 150, 200 bucks, depending on which module it is. So it has become more affordable. It's a subscription, so one should not forget to cancel the subscription. However, it's not an annoying one where one has to send a million letters or fight one's way through a big phone robot and chain in order to get to the person to cancel the subscription. It's really on your account. You can just say, I don't want it anymore. It's a button to click and then it's turned off. And once you need it again, you turn it back on again. So that, I think, has been done very well, but we can definitely together approach Pix4D and see if they would do something for the network.
Thanks, that sounds well.
Just in order not to deter everyone from using it. That's the quickly about what you need in terms of processing hardware. If you tried the exercise, you may have already stumbled across this part and were like, oh dear, I can forget about the exercise right away. Best is if you have a Windows machine, some of the software, and that's, I'm not talking Pix4D, I'll introduce you to a couple more in a second, but most of them are running on Windows operating systems. It's always an advantage if you have some graphical processing, this type of GPU, graphic processing unit, which can be just in NVIDIA or so, doesn't need much actually, but enough CPU. So 8 or 9, and you need enough RAM to process. Otherwise, it just takes very long. And if it takes very long, you risk that the computer crashes while processing, and then you start from scratch again. So that can be a bit painful. Here are some ideas around the project sizes. Small projects of under 100 images at 14 megapixel camera give you around 8 gigabyte, will need around 8 gigabyte RAM to process and 15 gigabyte free SSD space. If it's not SSD space, then just on hardware. There is just a problem that, or it's not a problem, it will just take more read and write time if it's not SSD. For medium projects between 100 and 500 images, you're at 16 gigabyte RAM and 30 gigabyte of free space that you require with a 14 megapixel camera. Large projects, you quickly end up needing 32 gigabyte RAM, 60 gigabyte free space, etc. If you don't have access to this type of hardware, then feel free to use any of the cloud options that are being offered by these companies. I know that Pix4D is working with Amazon in that sense. I'm not sure exactly what others are working with, but it's similar. So we've been looking now at Pix4D because they had a nice setup, and I think it's easy to learn from that one. Then you don't have to stick to it. There is a Metashape IGSoft, Drone Deploy, ArcGIS Drone to Map. If any of you guys run Esri licenses in your NGO, maybe they make you even an offer for the drone to map part, where basically that's what we just did now, same software. It's just the engine version that ArcGIS is paying for with Pix4D. They have a partnership, and then you process directly within your ArcGIS environment. Skyline software is also one, but I think that one's more advanced, more on the expensive side. And then there is Open Drone Map as well. Drone Deploy, for example, is cheaper than Pix4D, a bit slower, but it might do the purpose as well for all the projects that we would have upcoming. And there might be more out there. There is a catalog, and you will receive it with with this PowerPoint as well. It's geomatching.com. It's a large catalog of GIS software, not just GIS, but anything that requires geospatial something. That would be on that list. And it's really a big catalog. It's a bit painful to work your way through, just because, there are so many little modules and things, but they usually don't cover all of it, just a part of it, and then you have to switch again to a different software, etc. That's why it's nice to have one that is a bit one system, and one can stay within one environment. It's easier to comprehend and to keep your things together. And I just wanted to go through some examples with RGB. So this type of data is, for example, used in surveying with the RGB data and the good cameras delivering centimeter accuracy at a very high precision. There would be, for example, be mountains or villages, also dam structures in mountainous areas will be possible, or then road surveys. In agriculture, drones are used more and more as well, especially with sensors that cover more bands than just RGB or even thermal. So that's where we have the multispectral data, and where they look at the NDVI, that was the vegetation index we quickly looked at last time, to better understand the state of the crop in the field. which they call crop monitoring or scouting, using that data then to understand how much fertilizer needs to go where in the field. Crop protection, insurance purposes, one could fly and analyze how much of the area was inundated and has then proof for that, any drainage issues, etc. And there are, of course, all the solar, heat loss, and search and rescue applications, as I described earlier on a little bit already. Thermal sensors are quite common there, although it's not always easy to spot something through a thermal sensor, depending a bit on its thermal resolution it has and the ambient heat around a certain area. And then, of course, infrastructure monitoring with drone data, doing maintenance analysis, trying to understand what is working on a power line structure or pole. GNS network and mobile network antennas can be a challenge as well. Instead of sending a human up climbing any of these towers and putting themselves into a potentially dangerous situation, it's of course much more attractive to send basically a robot where that we can use to see and hopefully analyze and better understand what needs to be fixed. Or then, of course, more our direction, wildlife, land cover, and surface changes. So monitoring wildlife or understanding what wildlife is doing or where it is. So here you might be able to see the couple of rhinos under the bush here. Here, a environmental project where it's about protecting that little bog area, or then understanding what's happening with the glaciers up in the mountains, monitoring those. Of course, this is done by large institutes already, but also those somehow go back, or often go back to using this type of drone data to get a better 3D model and understanding of the situation of the glacier. Yeah, and with this, I reached the end of the presentation, and I'm happy to answer any questions that you might have.
No questions.
No
All
questions.
satisfied. Huh?
All satisfied, or everyone confused and too complicated? I don't know.
Or maybe a little bit of a mix of both. That would be the case with me, huh, Andrea? Because, of course, I'm not the professional as you are. You know, that's the drones. You know, that's your daily bread. I could say. You know, it's not mine. So it was fascinating to get this glimpse from your presentation. I enjoyed it very much. Thanks a lot. Comprehensive, covering so many aspects, but covering many aspects. That's why probably, you know, we need to digest it as well, you know, now at the end. Huh? But please digest it and dear all, you know, just provide a feedback. This helps us a lot, you know, and even we could, if there are open questions, we can integrate that in the last webinar, or then do an additional one, you know, just a Q&A webinar. So use this opportunity and provide your feedback. And I think you see it. I put the link in the chat. Again, you know, copy it, fill it out. It doesn't take a lot of time. Many of you have already done it. You know, it's really not more than 5 minutes, and it helped us. Coming to an end, and Georg is still here. That's great. Please, Georg, you know, the next webinar is on landslides. What will we look at exactly there? Can you give us an outlook, please?
Sure, Tony, thank you. Well, first, we have to check your homeworks. We discussed as the first example, a first exercise we mentioned during the last webinar. Then to finish flooding topic and then go straight to the landslide topic. And there we can use the products of the drone processing, like the digital elevation model, among others. But you can also do your hazard analysis for landslides without drone data. So there are different ways to get to the end or to the product. So that will be the topic, to know the working steps for landslide hazard assessment, which is, I said, more comprehensible than the flood topic. So yeah, that will be the content of the next event, and happy to meet you there.
Okay, thanks a lot, Georg. You heard it, and I heard while you were saying it, I heard the bell ring, 3 o'clock. So pretty much on time today. That's great. Thanks a lot, Andrea, for the presentation again. Thanks to all of you for participation. And I'm looking forward to seeing you in 3 weeks' time on Wednesday, 24th of May, for the last webinar module of this first part. Thanks again. Bye for now, and have a nice day or evening for our Asian colleagues. Bye-bye for now.
Thank you.
Bye.
Bye bye.
Thank you. Bye.